Okay, so now we will talk about another ensemble technique, which is boosting. Okay, so boosting is one of the most popular as bagging that we have already talked about bagging. Just I will recapitulate something about bagging that is necessary. Okay, so we have talked about bagging and now we will talk about boosting, which is one of the technique of ensemble learning, and I really hope that you will enjoy this section. And in boosting we'll talk about something called as gradient boosting and then I will just give you a geometric intuition, or I will just show you the implementation of adaptive boosting, which is often called as AdaBoost. Okay, then I will talk about extreme boosting, XGBoost. Okay, so these three algorithms means XGBoost works best in some cases. XGBoost works best. Okay, so gradient boosting also works best, but it is also works best. So we will see these three. Okay, so let's start with this tutorial, but before that I just want to tell you that you can do the problem set which is on GitHub, and you can subscribe the YouTube channel just by going to the https://youtube.com/c/newera, because this highly motivates me to make content like this for you all for absolutely free. Okay, so you can go to this New Era to subscribe this YouTube channel. It's 500 just I have 500 subscribers. Soon putting a deep learning tutorial. There's an announcement coming up soon, putting a deep learning tutorial soon. Okay, so let's start with this tutorial. And okay, so first of all, what is bagging? What is bagging? That we have already talked about. You can rewatch that bagging section if you want, maybe in a fast way. So bagging, we have low bias model, and high variance models. Okay, so our base models usually have low bias and high variance. Low bias and high variance means our base models usually have this low bias and high variance, and using bagging we reduce high variance, we reduce this variance. Okay, so our output will be, after applying bagging, we have our low bias and low variance model. Okay, so what we were doing in bagging, we are just simply doing the column sampling as well as the row sampling. Means we are doing the column sampling as well as the row sampling in case of random forest, but it's just take an example of random forest, and then we do the aggregation. Okay, so that's what we are doing. And let's see just a recap what we do. We have this large data set, DN, and then what we do, we simply divide this data set into subset of a data with the replacement. So I hope that you remember what is breadth replacement, that the data which is here, the data points which is here, it needs not to be different here. It can be same in the second data set also. Okay, so you sample endpoints, then you again sample endpoints with the replacement, then you sample endpoints. So you take in three subsets of your data, and then you train your model onto this data, like M1 onto this data, maybe logistic regression, maybe linear regression, or maybe support vector machine. So you have three models, and then if it is a classification problem, you simply take the majority of votes that this particular example is of a particular class, or if it is a regression problem, then you do the average or you take out the mean or a median. Okay, in case of regression. So that's what we are doing. And in random forest, these are called our base models, and in random forest we have our base models as a decision trees. Okay, so this usually helps in reducing your bias, Okay, so that's the bagging. So let's see what we have in boosting. Boosting is just opposite in case of bias and variance trade-off. So just now I think that you know why we have learned bias and variance a lot. Okay, so in boosting we have low variance, in this case we have high variance, but we have a low variance, high bias model. Here our model is underfitting. We have high bias model. Okay, so it is not performing well on the training set. Okay, so here we have a high bias model. And then what we do, we additively combine. Additively combine. What do I mean with this? This is a very great question. This is what we do. And here in bagging, we are doing the randomization, we are doing the bagging, means column sampling, then row sampling, then we have aggregating the model. Okay, but in boosting we have additively combine. That here it combines the weak, it converts the weak learners, weak models into a strong model. Okay, so different weak model tends to be a great model. Okay, just we will see how it tends to be a great model. So it is just combined. So let's see the core idea. So the basic idea of using boosting is to reduce bias. If you have a high bias model, then you likely to use boosting to reduce the bias of that model. Yeah, there is some other techniques also that we have already seen, but it's just we use boosting to reduce the bias. Okay, so let's see the basic intuition about boosting. So let's take an example that you have your data, you have your training data. So I'm just writing my training data. Where do I write here? You have your training data, which is your training data. I'm just writing train D. Okay, which is this is a supervised learning and a supervised learning technique. So you have xi and yi which is a label, and it goes I equals to 1, or we can write I equals to 1 all the way down to the maybe m. Okay, here m is the number of training examples into that training data. Okay, and then you make a model, m1. So let's take an example that we have made a model m1 that's simply a function f of x, which is our hypothesis. Okay, so now what we will do, this is the core idea behind boosting. So we have a training data, you have your training data, like which is your training data, and you train your m1 model onto that. Now what you have seen, you simply take out the error. Means the cost function, the loss. Okay, loss for ith example. So for each example you have yi, which is a ground truth, minus your model predicted value. Model predicted value is f of x, which is when you input x, then you get your output. So model predicted value is f of x. Okay, this will give you the loss. Okay, the loss for if it is 0, then it is very good. If it is large, then it is very bad. Okay, so here we are using just a simple regression loss, means just a loss. So if you add a summation over here, I equals to 1 all the way down to the m y I minus f of x, then this is the like MSE, but you do a square in MSE. But now because of the gradient descent to effectively compute the derivative, but here you can just see just as a simple conversation what we we are taking the loss for each training example. So here let's take an example that we have taken a loss, and then what we do, we train our model onto this loss. Means we train our model to reduce this residual error, error. Okay, we only focus, or we more focus onto the data which is misclassified or which has a very large error. Okay, so we focus on that. Okay, so what you do, so you want to reduce this error. So how you want to reduce? You want to make a model m that is given xi, means you fit this residual. So let's take an example. I'm just going to take an example to make you this statement clear that what you do. So let's take an example that you have a regression problem statement. So you have a regression problem statement. Oops, I don't know why I'm making a bad. Yeah, why my x-axis is not working great. Yeah, here is my x-axis, a bad x-axis, and you have an x like this, and then what you have fit in maybe this line. okay, a straight line. So here for this training example, the loss will be very high, so it will more pronely start focusing on that, and it fit on that residual covering this. Okay, so maybe it will do like this. Okay, it will also cover this if the residual is very high. So it always tries to minimize that residual. Maybe it can make a either the example is too much lengthy, but either it can make a non-linear hyperplane. Okay, so what we do, we fit our error. So we make a model M1 that minimizes the error by fitting onto the error. So here is where Li for I equals to 1 all the way down to the M. Okay, for each training example we are fitting a model. Okay, so it is more pronely focusing on the data which is either misclassified or which has a high the particular MSE or MAE. Okay, if it is a regression problem, then we take MSE or which is misclassified. So it is more pronely focusing on that. Okay, so that's the basic intuition. So let me make you the full equation how it looks like. So you have f of x with k means and some just a model, a big model means f of x. Okay, for each training example I equals to 0 all the way down to the k. Okay, all the way down to the k, you have one alpha times your model, ith model. So you will not only have one model, you have in first model that fits some, that second model that covers that fits that residual, then third model that fits that residual from this model, fourth model that fits that residual from this model, means error. Okay, so we have a different models. So we have a large model, this k, and we go through each and every model with some just assume it's a lambda. So we have this just as of now, just consider this as we have computed this somehow. So we will see how it is computed. Okay, we will see when we learn about some gradient boosting. Okay, so just assume that we have some just a lambda, a constant. Okay, here this f of ix that is trained to fit the residual, from the previous model. Okay, from the previous model means this model, this M2 trained to fit the error we get on M1. Okay, so this model may have some different thing. This model is able to correctly classify the error from this first model. This M3 is able to classify the errors from the M2. So like that. Okay, so that's the basic intuition behind boosting. Okay, so I think that you have understood about boosting. So now this will end it up, this function will be ended up giving you low bias and a low variance model. Okay, but there is a problem. So you may think, hey Ayush, can you name a problem? Yeah, sure, I'm here to name. Okay, but before that you can take a break if you want, because it will just take more 1 hour to complete. I think so, it's my approximating time. So it will take 1 more hour. You can take a break, or you can do just a problem set if you want, but start with a section and then complete a section, then see the problem set, then see some challenges given to you in my GitHub, and I really understand that you will be able to do that. Okay, so here you have this one. First you have a training data, then you have a loss for each training example, then each model tend to fit the residual error given from the previous model. Okay, and in that way they end up being a low bias model. It's very good on training set, but there is a problem. The problem is that if it is too much good on the training set, means only 100% accuracy on training set, then what will happen? It will start overfitting. New training example will come, then it will able not to classify or detect a good prediction. Okay, so that's why we have to take care of how many number of base models, so that we have a lambda. With this we will understand this all. Okay, great. So we have understood this, and so the core idea behind bagging is not too much hard. It's just saying is we just use bagging. It's boosting. The core idea behind boosting is to reduce the bias. reduce the bias on the train, like that. Okay, this converts the weak learners into the strong learners, and here we have a good fine-tuned models which is converted into majority of votes and then in bagging, like that. Okay, so let's see. So that's the basic intuition behind boosting. So there are some of the techniques that we'll study about, like a gradient boosted decision trees, which is often called as GBDD. Okay, this is because in random forest we have our decision tree, and here in gradient boosting we have our base learners as a decision tree, and gradient boosting has a base learner as a decision tree, and then we have adaptive boost, which is often called as adapt boost, which is a little bit more advanced version of gradient boosting. Then you have extreme boosting, which is XGBoost. Okay, which is again a family of a good algorithm, and it's always outperform. It's very powerful algorithm, XGBoost, as I've seen so far, and I will show you the implementation of XGBoost also with some. I will show you how it is implemented and everything in this section only. Okay, so. And that's the basic intuition behind bagging, and I really hope that you understood bagging in detail. Just to recap that and why I'm saying bagging, it's a boosting. Okay, so boosting here, in boosting we have low variance and high bias model we additively combine in which we convert our weak learners into strong learners, and the core idea is to reduce the bias. It simply means that we want to improve our error on the training set. Okay, so that's the basic, and we have 4 which we'll cover in this section, which is gradient boosted decision trees, adaptive boost, then we have XGBoost. Okay, so I think that you understood about boosting. Okay, so now we will talk about gradient boosting, which is again a good, very fantastic, brilliant algorithm. Okay, so to just use in internet companies or very big companies which is used in ML in production. Okay, so which is usually launched in 20s, these algorithms. Okay, so we'll study in detail to make you understand each and every concept of gradient boosting, and then we will see the implementation, then we will see the adaptive boost, then we will see the XGBoost, and then we are end up with this ensemble models. Okay, then we will go with unsupervised learning techniques. Okay, so let's start with gradient boosting.